Yes, sir.
So today we will start with one more important concept what we look in our operational amplifier circuits, that is called as sample and hold circuit. I don't know whether you have any introduction to this in your analog electronics or not. I don't think so. Sample and hold circuit. The very name itself indicates what exactly this circuit is doing. Okay, samples the input for certain predetermined time, or samples the input at an instant and holds that value, right, for a certain period of time, right. So this is the meaning of sample and hold circuit, that is samples the input at any desired time, and next holds the input to the sampled value, holds the input to the sampled value for a predetermined time period. This is what is the meaning of sample and hold circuit. Now the question is, why do we need it, right? See now, one example I will give you. This you need not take. So you have something called as analog to digital converter, right? So which continuously keeps converting the analog value into its digital equivalent. Anyway, we will be studying about these things later. So here you provide analog input, and here you take the digital output in the form of bits or something like that, right? So now when your analog input is continuously coming here, let us say that this is the nature of input which is continuously coming, which may be some measurement, right? So speed, velocity, temperature, whatever it is, right, in a particular from a particular sensor, from a particular measuring instrument, these inputs keep coming, right? So when you want to convert these values into their digital equivalent, you know what, for the values are supposed to be converted into digital equivalent, you, for the purpose of processing, right, manipulation later, comparison, right, analysis, right, it is easier to have the values in the digital form. So now this analog to digital converter will take certain time to convert a given analog value into its equivalent digital value, right? So that is called as the time of conversion. It is not going to do this instantaneously. It has to be there for a certain period of time before it is properly read. That is the reason why we make use of the sample and hold circuit. That is one reason, right? So now suppose if you want to measure the analog input somewhere here, this is the analog input, right? So now we will have to keep this analog value till it is properly converted into its digital equivalent, right? So you have to sample the value here at this instant, and you will have to hold that value for a certain period of time, right, till it is processed further or it is converted into its digital equivalent. Sometime it is used in the modulation techniques, it is used in the communication techniques. So many examples are there as long as the sample and hold circuit is concerned, right? So this is one example or one instant where you may use the sample and hold circuit, right? So now let us try to see how exactly your sample and hold circuit can be realized from the point of view of circuit operation, where the objectives are very clearly known to us. So you have some analog input, it has to be sampled at any given desired instant, then the sampled value is required to be held for certain period of time. Then again the next value is going to be taken, and the next instant where it is supposed to be sampled, that will be known, and the process repeats depending upon our requirement, right? So to understand this, now let us try to look at the circuit diagram, wherein there are different approaches which are given in different books as long as the circuit is concerned, but please try to understand the concept behind it. So let us now look into the circuit. Here we have two operational amplifiers. Please write it down. Draw the circuit. So this is one, and from this you have the input being connected to one more operational amplifier. Of course, both the operational amplifiers here are acting as a voltage follower circuits. So this is a very important one, which is the capacitor, and here I use this as the voltage follower. This also is being used as voltage follower. And here I provide the analog input. The most important component here happens to be one MOSFET. Which is drawn something like this. So this is minus, this is plus, this is the supply voltage here, Vs analog input, and here I take it this way. This I call it as Vc. This is the capacitor, and this is my switch, or what I can call it as MOSFET. Again here drain, so this is going to be your gate, this is going to be your source as long as the MOSFET is concerned. So this is minus, this is plus, so this is what is your V0. This is a very simple circuit. In different books sometimes the idea is to make use of only one operational amplifier. That is also fine. So two operational amplifiers are used, because since it is a voltage follower, you will have always a better control. That is the reason why you make use of two operational amplifiers. This is what is my drain, D. All of you are noting down this circuit or not?
Yes, sir.
Okay.
Yes, sir.
Please note down. Now here we have the input voltages as well as the control voltage as well as the output voltage. We will have it like this. Understanding the waveform is very important here. This is Vs, this is Vc, and of course this is V0. One cycle I will draw. Here I will draw the control signals, something like this. Just one second, I will draw a dotted line here because this is not the actual output. Yeah, it is something like that. Later we will draw the output as per our requirement. Please note down how I have marked the values here. All of you are taking down. Is it over?
No, sir.
Okay. Okay, now look at this circuit. Our idea here is to make sure that the input value, okay, the input value is sampled at any desired instant and the value is held for certain time, right, before the next sampling instant occurs. So I have drawn all the waveforms which are required for our analysis except the actual output waveform, right? So let us try to see how exactly the circuit operation can be considered here. Let me, yeah. Okay, so now you can see you have got two voltage followers here. One is the first one, that is A1, right? So simply this is an whatever the input you are going to give here, right? So the output is same as that of input, right? So that means virtually here at this instant, okay, whatever I am marking here, that happens to be my actual input in this particular circuit, okay, and the very task of sampling and holding the value for particular period of time to that sampled value, that is being taken care of by this MOSFET. This MOSFET plays a very, very important role. All of you know that how exactly a MOS device works, right? Whenever I give the control voltage here, whenever the control voltage exceeds some value, let us say that this is the control voltage, right? Whenever the control voltage exceeds some value, the MOSFET will come into conduction. So that means when your VC is greater than V threshold, right, your MOSFET conducts. This is what is the known thing to you, right? So whenever you bring the VC below certain value, the MOSFET stops conducting. So that means we can say when VC is greater than 0, the MOSFET conducts. When VC is equal to or less than 0, the MOSFET is turned off, right? So this is what is the concept which we have seen as long as the working of the MOSFET is concerned. Now the same concept is being used here also. You can easily understand the concept of the sample and hold circuit here. So this is the input Vs, okay, so this is where you are having that Vs. So now as long as, okay, you apply a control voltage here, Vc, okay, when the control voltage is applied, your MOSFET starts conducting. So that means you have the conduction between drain to source, okay. When there is a conduction between drain to source, this capacitor is going to get charged to the supply voltage here. This capacitor is going to charge to the supply voltage, right? And since this is the output voltage, so you can see here the same voltage at source, this is the output voltage. Whatever you are having at input, the same value will be available at the output also, apart from charging the capacitor to the desired value. That means initially here, you can see here initially, so when I increase the input voltage like this, right? So as long as the MOSFET is conducting, that means from this instant to this instant, your MOSFET is on, right? Or your M is on here, right? So therefore your output also will follow the input. I will draw it like this. Output will follow the input. Now at this instant, right, so you are turning off the MOSFET because that is the instant at which your input is required to be sampled. So this instant, let us say that this instant, okay. So now for clarity, let me make this a little wider like this, so that you will have a clear picture here. So now when you want to sample the input at this instant, say this one at T1 for me, okay. So what happens here, you will turn off the MOSFET, okay. When the MOSFET is turned off, so the second operational amplifier A1 will be having a very large input impedance, as you know, right. So whatever the charge that you are going to have across the capacitor, it will be held to the previous value only. That is, see here, this is the second time where you are going to sample, okay, between these two instants, so your input value is going to be held to this value, okay. This is what is sampling at T1 and holding the sampled value till the next sampling instant comes. So it could be here or it could be here. So sometimes this may be displaced here, this may come earlier. That all depends upon your requirement, where exactly you want to catch, or specifically speaking, latch that particular input value, so that it can be held for certain time period, so that it is processed for whatever the application it is deployed for, okay. So now up to here, up to this instant, the input value will be held, okay. Then suppose after this, okay, this is the value which you want to hold up to this period. Then after that you are going to make the input to appear as it is. So therefore again you have turned on the MOSFET here at this instant. The moment the MOSFET is turned on here, so your input is continuously increasing here, as you know, it is increasing like this. So at this instant, again till here, till this point, you are going to have the input. Then again you can see here from this point to this point, okay, because of the presence of this, you will hold it like this. Check whether you are going to hold it like this now. No, please check the input waveform. So as long as the device is on, the input is on. As long as the device is on, the input is on. Correct, right? So here you will hold the value for some more time till, say, this instant. Then after that, whenever this is on, you are allowing your input to present across the output, okay. Then from this instant to, you can see here from this, yeah, this instant, you will hold it, and again you can see here, you will come up to this point, okay. Then you will hold it for some more time here like this, right, and it will keep going like this, right. You can now, from this diagram, you can see where exactly you have the input as it is. As long as your M is on, when M is on, your output will follow the input. You can see here the output will follow the input, the white lines, as long as the M is on. But once M is off, you can see the red lines, right. So where your output will be held to the previously sampled value, either it is here or at this instant or at this instant or at this instant, till the next sampling time will come into picture. So now if you continue to go like this, right, so you will have the input again from this point to this point. So this is what is going to happen as long as the sample and hold circuit is concerned, right. So now this is the sample time here, the time required. So what you can call this as TS, and this is called as TH. TS is referred to as sample time and TH is called as the hold time, right. So now there are certain important conditions to be fulfilled here, otherwise your circuit will not work precisely. What exactly are those conditions means? Now see here, whatever the capacitor is charging here, okay, it will be having a charge or the time constant of charging, right. So before that, let me quickly write some of the things here as per our requirements, right. So I will take it here. So now VC is the control voltage, right. So MOSFET, I will write it as M. M is on when VC is greater than 0. M is off when, let us say, your VC is less than 0, right. So when M is on, output follows the input. Am I right or not? When M is on, the output follows the input. C is charged to the instantaneous voltage level, instantaneous input voltage level, right? So now to hold this value, M is made of, M is made of. So to again sample the input, M is again made on, right? And the process repeats. This is what is the working of the sample and hold circuit. But one condition, whatever I have told, right? At what rate your capacitor gets charged to the input voltage is given by the time constant. The time constant of the capacitor charging. So what could be the time constant here? It is the R naught, that is the output resistance of this amplifier A1, because it has to charge from here, right? Plus RD on. What is RD on? Can anybody tell me? RD on, it is the on state resistance of your conducting MOSFET, correct or not? So now if you take the equivalent circuit of the charging path here, the output resistance comes here for A1 plus the on state resistance, the conducting resistance of your MOSFET, and of course the product of this summation of this resistance and the charging time constant of the capacitor. So this is what is the charging time constant of the capacitor. But here one more important point to be noted here is the very nature of the capacitor. So your capacitor should hold the charge like this. Just now I have shown you. So whenever your input is going like this, at one particular instant the capacitor should hold the charge like this, right? So holding of this charge may be something like this also, because there may be some leakage phenomena associated with this capacitor. Leakage means what? The capacitor should hold the charge. Ideally it will hold the charge, means the output will remain like this. Output has to remain like this, right? But because of the bad dielectric nature of the capacitor used, or the very nature of the materials which are used in the capacitor, right? Or there may be a small discharge in the forward path also. Though this resistance A1 has got a very high resistance, but it is not infinite, right? So there will be a very small leakage current in the forward direction also, right? But which can be neglected. And there may be a small leakage in the reverse direction also. So whenever the MOSFET is conducting, it will be having a very small reverse leakage current also, right? So it may flow from this source to drain. So all these things matter, whether your charge is held to this value, or it may be like this, or it may be like this, right? So ideally speaking, we want to have the holding time, right? During the holding time, the capacitor deployed holds the charges firmly, like that. Here we cannot use the ordinary capacitors for the purpose of the sampling and holding, especially when you require the sampling to be very precise. So there are different capacitors deployed which have got very low leakage factors, or very good dielectric constant or something like that, right? So here the capacitors used, you can write here, Please write it down. The capacitors used, the capacitor used should have very less leakage, good dielectric property. Only this much is sufficient for you to understand these things, right? So the capacitors used should have very less the leakage, and it should also have very good dielectric property, right? And of course whatever the A1 and A2 we are having here, so this should be A2, okay? So whatever the two operational amplifiers we are having, right, so they should have very high input impedance, right, and very low output impedance in order to meet this particular requirement. And whatever the MOSFET we are going to have here, that should also have very low reverse leakage current. So when the reverse leakage current is very low, then only it is possible for you to retain the capacitor, charge across the capacitor. So these are some of the important conditions that are required to be satisfied as long as the sample and hold circuit is concerned, right? And there are some dedicated ICs as long as our operational amplifiers are concerned, which are totally meant for the purpose of this sampling and holding, right? So I will just give you one diagram here. Dedicated Opamp based sample and hold circuits, right? One simple diagrams, it is just for your understanding. Again, it is given in your book also. So it is I think LF, if I remember correctly, LF 398, right? So this is the operational amplifier, right, which is very much meant for the purpose of sampling and holding, right? So you just see here how exactly this circuit can be realized. So this is something like this. This is my VC and this is my V0. I need only three things here: one control voltage, and another is your input voltage, and of course output voltage. And you have one provision here, that is here to connect one external capacitor, right? So here we have got plus VCC minus VEE. Okay, the other pins I am not going to mark, that is not required for us, right? In fact, pin number 3 is V in, and pin number 8 is your control voltage. Between 7 and I think between 7 and 5 you have this capacitor connected, and VCC, this is 1 and 4. So this is what is the operational amplifier. In fact, this is LF398. It is a dedicated IC, operational amplifier IC, so which is meant for the purpose of sampling and holding. Now you can see here you have got the built-in MOSFET also here, is it not? Because we are applying only the control voltage, we are not finding any MOSFET here, right? So the control voltage has to be applied externally, and you will have to connect one external capacitor here again, which holds or which meets all the requirements as I have just mentioned there. Okay, so this is called as the dedicated operational amplifier based sample and hold circuit using LF398. So whatever A1, whatever A2 we have seen in our previous diagram, right? Whatever the MOSFET we have seen in our previous diagram, all those things are built in here, except you have to give a control voltage and of course a capacitor in order to make sure that the sampled value of the inputs are held for the required period of time, like this here, whatever we have seen. Okay. I hope you have followed this. The working is very simple here, right? As long as your control voltage goes above 0, right, the input will follow, sorry, the output will follow the input. At any desired instant, if you want to sample and hold that value, right, you just have to turn off the MOSFET. Once the MOSFET is turned off, the capacitor holds that value. The held value of the capacitor is retained as long as the capacitor satisfies those properties, right? So that value will be remaining there, which are indicated by these red lines here, right? Again, if you want to go to the next sampling period, you can definitely go with the turning on of the MOSFET, and turning on and turning off of these MOSFETs will switch the output between the input values and the sampled and held values. This is what is the working of the simple sample and hold circuit. All of you have followed it or not?
Yes, sir.
Fine. Okay. So now, as as a part of this sample and hold circuit, let us try to discuss about one more simple concept here, which is referred to as peak detector. This is again another philosophy. These are all very important practical applications if you want to carry out some simple projects and all, right? So let us say that the temperature is continuously being monitored in a day, right, for 24 hours. You know, the temperature is an analog quantity. You have got a temperature sensor, and you get the temperature output in the form of the voltage level or something like that, right? So if you want to know the maximum temperature measured in a particular day, right, so that is where you can make use of the peak detector here. Okay, so which will give the maximum value, something it is taking place like this, your input at any given instant, what exactly is the maximum value. So it is the maximum value here. Here it is more than this. So here it is less than this. This may not be possible for us to use until we make some changes in the circuit, and in all this probably this is the maximum value. So this is the value which is going to be recorded there. So this is called as the peak detector. Now let us try to see how a simple peak detector can be realized using the operational amplifier. A very simple circuit here, right? You please note down. You have, in fact, I should have taken this peak detector before I discussed about the sample and hold circuit. Peak detector will be a part of your sample and hold circuit, may not be directly, indirectly. Yeah, I have a diode here, very simple. Now I will bring in one capacitor here, that's all, and this is the circuitry which I am drawing with a dotted line. Is used for the purpose of identifying different peaks. So this is VCC plus VCC, and this is minus VEE. Now you will understand how exactly this peak detector is used for detecting the peak values. Especially, listen to me, there are certain cases wherein you may not always have, the sine waves, right? You may have the triangular wave like this, you may have the sawtooth waves like this, right? So you may have the square waves like this. So your multimeters, whatever you have used in your laboratories and all, so they measure the RMS value, right? RMS value of the output voltage or current, whatever it is, whatever they show, whatever they display in terms of the numerical values, they are always the RMS values. But sometimes you may need to find out the peak value of your input signal, right? So those kind of provisions also can be given in your multimeter, so that instead of measuring the RMS value, your multimeter or your meter, digital meter, should be capable of measuring your peak values. In such cases, you can make use of the peak detectors there only. You can have two different options. One is to measure the conventional or the RMS value. You can also find out the peak value, right? Like that, there are so many type of multimeters available nowadays, right? So this is another example wherein you make use of the peak detectors, right? So now, how does it work? If you look at the input and the input signal Vs, right, which I consider a randomly varying input, something like this. Let me say that this is my Vs. I can consider it for anything, okay? So how does the circuit work? So when the diode is forward biased here, can anybody tell me when is the diode forward biased? When Vin or Vs, when Vs exceeds Vc. Let us say that there is a small voltage across the capacitor or the output voltage, right? So your D is forward biased. Then what happens? The Vc, the voltage across the capacitor, will be Vs. This is as simple as this. Okay, this is as simple as this. Now, due to some reason, if your Vs falls below Vc, here, this is very simple. If your Vs falls below Vc, let us say that somewhere here is the Vc, right? So what to the maximum value what you had here across the capacitor, that will be retained, because your diode will be reverse biased now. The diode will be reverse biased. So once the diode is reverse biased, to what previous value it had reached, that value will be retained across the diode. And again, when it exceeds this Vc, then definitely the diode will again become forward biased, and Vc or the capacitor will be charged to the next value, right? So now once it comes down, then again the voltage will be held here, and it keeps repeating till you have the maximum voltage recorded as per the capacity of the input voltage as well as the capacitor. You cannot have the indefinite value of the voltage, right? Here they are all physically limited by these things, right? So now here, suppose if you want to measure one more value, that is, say here, okay, I have gone here. Now let us say that here I have got one more peak, something like this, right? So it is not possible for us to measure this because the voltage is already clamped to this value. For that reason, I can have a switch here, MOS based switch. That means if at all you want to discharge the voltage across the capacitor, you can discharge to the required value, and you can make the capacitor to get to the other charged values here. So this is what is the working of the peak detector. This is, again, of course, it is not there in your curriculum, it is beyond the curriculum, but this is a very important component in your curriculum, because there may be so many practical examples of the peak detector which can be realized with the help of such simple circuits or such simple designs. You don't have any resistance here, one capacitor and one diode. Diode will simply take care of whether the input is greater than the voltage across the capacitor, or the voltage across the capacitor is held to the input value or not. Only that much will be taken care of by the diode. Okay. So this is about the peak detector. In order to identify the peak value of a continuously varying analog signal, I already told you where this particular circuit can be considered as a practical application, right? So in the meters where there is no provision to measure the peak value, which in turn measure only the RMS value, if at all you need to find out the peak value, you can make use of this. Okay. So this is about the peak detector. So that in fact virtually completes this particular topic, the third topic.